Welcome back, everyone. The talk will begin shortly. Please take a seat and make yourself comfortable. So, hi everyone. For the third talk of the day, we'll welcome Dr. Ma Jingyi, who was born and raised in Penang. She got her degree in physics at the National University of Singapore. During her final year as an undergraduate, she participated in the Astronomy Summer Internship Program offered by the Academia Sinica Institute of Astronomy and Astrophysics in Taiwan. Starting from that point, she is acquainted with astronomy research and worked on a project related to planetary dynamics. Curious to learn more about the planets, she enrolled in a master programs at the University of Hong Kong and later went to Tokyo Institute of Technology in Japan for a PhD. Since she is now a postdoctoral researcher at the Max Planck Institute of Astronomy, working on planet formation theories using numerical simulations. The topic of the talk that Dr. Ma will be giving is the flavorful exoplanets and how is to form them. Ever wonder how exoplanets are detected and how do we measure their physical properties and how they form? Lucky for us, Dr. Ma will be giving us an overview of the current state of the art. She will highlight interesting discoveries and demonstrate how astronomers bridge the gap between observation and theory. Without further delay, let's welcome Dr. Ma Jingyi to the stage.
Can I remove the mask? Yeah. Cheers. Thank you. Hello, everyone. I would like to thank the organizers for the opportunity to speak here at this very wonderful event. So this talk will be on planets, which is what I like. So we will start with planets in our solar system. I hope most of you are familiar with the planets in our solar system. If not, here's a brief, quick overview. So we have 4 planets close to the sun. These are planets made mostly out of rocks, so we call them rocky planets or terrestrial-like planets. Okay? In case you're wondering, we are the 3rd from the sun. Then further away, we have Jupiter and Saturn. These are planets made mostly out of gas, and they are very huge, so we call them gas giants. And the furthest away, we have Uranus and Neptune. These are also giant planets, but they are in a region so cold that most of the material already condensed into ice. So we call them ice giants. And further away, we have a myriad of very small objects here for illustration purposes. So these are the objects in the Kuiper Belt and the scatter disk and the Oort cloud. So if you look up at night, you will notice that we are not alone. So this is an illustration showing that in the solar neighborhood, we have other stars. So that means we have neighbors. So if we have neighbors, you would wonder that, do these stars have planets around them? And do we maybe have another Earth? So these are the questions that are puzzling people. And we can tell you that there are actually planets around all these stars around us. So one of the star systems that I will highlight today is this tiny one over here. It's called 51 Pegasi. It's very famous because around this star, in 1995, that is 28 years ago now, so we discovered the very first extrasolar planet orbiting this star. So we call it 51 Pegasi b. You are wondering why it's B and not A? So A refers to the star already. So the first planet to be discovered is called B. Then the next we C, D, E, F, and so on and so forth. So this planet, 51 Pegasi b, is a very large planet. It is about half as massive as Jupiter. That is about 150 times the mass of the Earth. This planet is very close to the star, so it goes around the star every 4 days. We call it hot Jupiter. So because it's very close to the star and it's very hot in that region, therefore hot Jupiter. Okay, so this discovery is important enough to be awarded the Nobel Prize in Physics in 2019, which is like decades after the very first discovery. So you will see why later. So how is this planet discovered? It's discovered by a telescope on Earth, so using a method called radial velocity. What is radial velocity? Radial velocity refers to the movement of the star when there's a planet orbiting the star. So the illustration shows you that the whole star is actually not stationary, but it actually moves around the center of the gravity between the star and the planets. So from the observer's eye, so if you were to observe 51 Pegasi b, 51 Pegasi, it will be moving towards you and away from you, doing this motion. So when it's doing this, the light from the star changes color. So when it's closer to you, you will see that it appears bluer. When it's moving away, you will see that the light appears redder. So if there were no exoplanets orbiting this star, the star would appear stationary to you. There will be no changes in the starlight that you see. But when we observe this motion, then we can deduce that there is an exoplanet around this star. And this method is only good for finding very big planets because the motion of the star then will be very big. If it's Earth orbiting the sun, you might not see anything, okay? But we are obviously very curious. We are not stopping with just one exoplanet. So there are further missions to send telescopes to space with the objective of discovering other planets like the Earth. So this is a famous one, Kepler Space Telescope. It was launched in March 2009. The objective is to find Earth-sized planets around other stars. So Kepler was a space telescope, so it launches into space and start looking at one point of the sky and try to find as many planets as possible. So the method used by this telescope is called transit. Transit finds planets by looking also at the starlight, but they are searching for if any stars, the starlight dims. That means the brightness of the star reduces at some point of time, pointer not working, reduces and goes back to normal again. So if there were no planets orbiting this star, okay, simple assumption, so the brightness will not change with time. But if there's a planet, fortunately, passing through in front of the star, like this, so you see part of my face is blocked. If this happens enough times, then you know that something is going about the star. So with this method, we can get very precise information about the size of the planets. Because we know the size of the star, then we know how much light is taken away during this transit event. Then there's an equation to calculate the size of the planet. So everyone, today, as of January 2023, we have discovered and confirmed more than 5,000 exoplanets, 5,000 other Earths out there, 5,000 other worlds out there. You can let your imagination run. So what are the types of the exoplanets that we have found today? So a bit surprisingly, we actually don't find that many planets like the Earth. Only 4% of the planets that we find are similar to the Earth. in composition. That means they are made of mostly rocks. So most of the planets that we find out there, these extrasolar planets, they are mostly made of gas, like Jupiter and Saturn, or they have a lot of ice in them and some atmosphere, like Neptune, or they are what we call super Earths, so bigger than Earth, made of rock. So super Earth is interesting because it doesn't exist in our solar system. So 5,000 planets form. We also find systems with multiple planets. So most of the exoplanet systems that we find have at least one planet going around the star, but some of them, they have more than one. And this one, TRAPPIST-1, is my personal favorite because I worked on this during my master's degree. So it has seven planets, but all of them are the size of the Earth. And all of them are so close to their star that you need to fit this whole system inside the orbit of Mercury. So Mercury goes around the sun in 88 days. These guys, they go around their star in one, or I think one, yes, a few, less than 1 day and more than 1 day, roughly like that. So very fast. And the interesting thing about this is, if you look at the colors, there's red, green, and blue. So what does these mean? Red means that these planets are really, really hot. Blue means these planets are really, really cold. And green means this is the right amount of temperature so that water can exist on these planets as liquid. So we are very happy to find planets like these because we want to understand how the Earth came to have life. So then people thought that if you want to understand more, maybe you need to look at other planets that also can have water on them as liquid, not ice and not evaporated into the air. And it gets more exciting. So this is 1 year ago already. In Christmas 2021, a new space telescope was launched. It's called James Webb Space Telescope. This will be the future of planetary science, exoplanet science as well, because with technological advancements, we will be able to see more than we know. So James Webb has been sending data back already in July last year. So James Webb is so good that it can tell you what exists in the atmosphere of an exoplanet. So this is the spectrum from WASP-39b. It's another exoplanet. So it's a gas giant, so it's easier to look and see what's inside the atmosphere. And they found carbon dioxide. So they also find water, but I didn't show. The plot is really similar. So this is just to show you that this is just to illustrate how advanced we are now. This is like saying that this is the exoplanet WASP-39b, and you are looking from there, and you are just looking at the top of this thing, and you can say, I saw carbon dioxide. I think this is a really remarkable achievement. So we'll be waiting for more and more information and data from the JWST. So, having told you a bit about exoplanets, what's interesting about them, here comes what I do every day. So it's actually standing in front of a computer trying to figure out how planets form. So here's an overview of the very bigger picture. So we start with an interstellar cloud of gas and dust. From this gas and dust, it collapses at some point and it forms our sun. Then around our sun, a disk of gas and dust, like the roti canai, will form around the sun. So from this material, from the material in the protoplanetary disk, which is the dust and the gas, the planets were formed. So you say, well, that's it, right? But actually, we are more curious than that. We want to know what goes on in the process. So we will start with protoplanetary disk. Here is a real protoplanetary disk. This is HL Tau. This is observed in 2015 by a telescope on Earth in South America, in Chile. It's called ALMA, ALMA, Atacama Large Millimeter Array. So this is a nice picture showing you that protoplanetary disk, and it's good enough to show you that there are rings around it. So there are bright areas and there are dark areas. So the brighter areas means the concentration of material is very high. So this is actually the image of the dust around this star. So protoplanetary disks, they have gas and dust, but we can only see the dust. We cannot see the gas. Okay, but they comprise of only 1% of the total mass of the disk. This whole thing, see here, is 1%. So this is a question for you. Where is the other 99%? Yes, I heard the answer. Gas? No, gas plus dust is 1%. So remember the cloud, when they collapse, you form the star, then you form the disk. So if the disk is only 1%, then the 99% must be in the star, correct? Very good. Maybe John can give out prizes later. So, okay. Saya bukan cakap sahaja. So, in PDS 70, 3 years later, we actually observed a planet forming inside the disk. So this is really cool observation that shows us that planets really form inside the disk from the material around the star. Okay, so the planet formation process, here it goes, can be summarized in one slide for everybody. So it is essentially the continuous growth of small materials, the dust in the disk, becoming bigger objects called pebbles or planetesimals, then slowly becoming even bigger objects like the size of our moon. We call it protoplanets or planetary embryos. Then from this on, something will happen to give us either a rocky planet like our Earth, or you can be even bigger to the size of Jupiter. So I will walk you through step by step this whole process. And hopefully by the end of this talk, you will understand a little bit more about how planets form. So step one, we need some dust. So in the disk, there's a lot of dust and there's a lot of gas. But for the moment, we will not talk about what the gas does. So we will only look at the dust. So dust is really tiny. Okay? If you have done some housework, you know that it's pretty annoying to clean your house every day because the dust is always there. So dust, in space, they will collide and coagulate. They collide gently and they stick together. This process will continue. They will continue to grow and grow until they reach the size of about 1 millimeter or to 1 meter. So these kind of objects, we call them pebbles. Pebbles, we don't have a good image of pebbles from space yet, so I will use pebbles as we think of it on Earth to illustrate the point. So it just represents material that is millimeter to meter size. So what happens to the pebbles? We want them to grow bigger, but they cannot because there is something blocking them from going to a larger size. So from when pebbles, you want them to stick together, but unfortunately, the collision between them is really strong. When they try to collide, they don't stick. They actually break up to become smaller pieces. So we called it the meter-sized barrier because they cannot cross over this barrier to become a bigger object. So how do the bigger objects form then? Because we have planetesimals, which are the tiny material before we reach the planet stage. So anything that's smaller, we give the diminutive of esimals, so planetesimals, planet yang kecil. We observe them today because it's the asteroid belt. It's the other material that is smaller. So they are there, so they must have formed somehow. So how did they form? So one idea is that they only form in certain regions in the disk. So from the disk, you see that there are bright and dark rings. So the brighter rings is the area where a lot of dust concentrates. Okay, these regions, we call them dust traps, or some people call it pressure bumps. So what happens in this area is that there's so much dust inside it that it's like a traffic jam effect. So imagine if it's a lot of cars coming in, and if it's so many cars, so many dust at once, then boom, the dust will gravitationally collapse, like how the cloud became a star. So the dust will form a larger object called planetesimals. So we skip over the step of the pebbles. So the dust can directly form planetesimals, but they don't do it everywhere in the disk, only in certain regions. Okay? So now we have planetesimals in the disk, not everywhere. Some special places we have planetesimals, but we have pebbles everywhere in the disk. So these planetesimals, because they are bigger, they can start to eat all these pebbles and grow big. This is like in a conveyor belt sushi. So the pebbles, like the sushi, is keep coming in. So you just eat, then you eat, then eat and grow. Then if there's a bigger person, so a bigger planetesimal which keeps eating your sushi, then you don't have enough sushi to eat, so you don't grow much. So then we can have some in the disk. Some of the material grows to a bigger size. Some remains maybe like this, the size of the moon or size of Mars. So we call them planetary embryos. Okay. Now we have the big guys and the small guys. So at this stage, we will try to just sum it up. So the bigger, the not so big guys, they can collide with each other, and they will form bigger objects. This is called giant impacts. Okay? If the planetary embryos, they eat so much pebbles that they are big enough, then they can start accreting. They can start eating in the gas from the disk, and they grow to become giant planets. So these are two possible ways of growing planets of different types. Okay, so this is to show you the summary again. So we are basically going from dust to giant planets. If you notice that we are actually going from micrometer-sized material to objects that are more than 10,000 kilometers. So this is actually not easy to study in real life, so we need the help of computer simulations to help us. So this is the summary. But this picture actually to us, astronomers, is fraught with questions because we actually don't know whether every of these arrows are actually correct. So what goes on here? Does it really work like this? Does it really go from here to here like that, as what I described? So every of this arrow is actually an active area of research. And furthermore, we don't know what goes on with the gas. So I'm nearing the end of my talk. So here's trying to tell you what we do day to day. So what we have actually is we have detections of planets. We observe exoplanets. Yeah, it is how much the mass, it is this size, it is maybe this composition, it has rocks, it has gas on it. Then the question is, how do you form them? How do you get there, right? So the question is, we have snapshots from here, then we have observations of smaller bodies. Yeah, we know they exist. Then we have observations of the disk. So this is like different snapshots of the lifetime. So what happens? But we cannot observe going from here to here. What we need to do is we have these information. We need to understand what happens at the beginning. So we use computers simulations to help us. And this is how we work. So in one of our models, we need to understand how big is the disk, how massive it is, what is the disk made up of. When I say what is the disk made up of, it's not saying it's dust and gas, but what is in the dust and the gas. So how much carbon is in the dust, how much nitrogen, other material, how much iron is in it, okay? And how long does the disk live for? So if it's a very short lifetime disk, so it goes away really quickly. So does it form planets in time? Maybe not, because it's too, it goes away too quickly. So these are all the questions that we don't know, and we are finding out the answer. And if you change the sizes and the masses or the compositions of the disk, you might get different answers from what we see today. So this is an ongoing effort to understand how planets form. And the challenge is we don't know what are the initial conditions. What should we put into the models to get what we want, to get what we see today, okay? So in the middle, I put two questions because we are also not very sure where do these pebbles and the planetesimals form. We also don't know how fast do they form, okay? So they also affect the outcome of planet formation. So we are trying to understand, we are trying to go from here to here with modeling. Then what the model outputs, the model will grow a planet for you, and you can compare your planet from the model to the observation and to see if they match. If they don't match, then you try again. If they match, then it means your model is good enough. You can try to understand how this planet came about. Okay, so here is the summary of my talk. I told you that we have found 5,000 exoplanets today. That's 5,000 extra solar planets outside our solar system. And they come in different shapes and sizes. They also have different compositions. Then I told you about how we think the planets form. So it's actually from dust to planets, and how astronomers study planet formation. So it's a combination of using observations and simulations. So that's all from me. Thank you very much.
So thank you, Dr. Marjini, for such an amazing talk. So again, I'd like to open the Q&A session. So if you have any question, just move to your nearest microphone and just ask Dr. Ma any questions.
Hello.
Hi.
Thank you for the talk. So I have this question about the word dust.
Mm-hmm.
Because in everyday life, dust is just dandruff and hair cells and stuff like that.
Yes.
But you kept saying dust and gas.
Mm-hmm.
So can I know the distinction? Because we know that in outer space it's mostly hydrogen and helium.
Yes.
So what is dust? What is gas? What is dust? And how do you guys differentiate?
Differentiate between them?
Yeah.
Dust, Dust is really, we can see them with telescopes. So we know we have hydrogen and helium, but we cannot really directly see the gas. But what we can really see in space is actually this cosmic dust material. What is that made of? Silicates. Depends on where you are in the disk, okay? If you are very close to the star, you are probably rocks or maybe even heavier stuff because the lighter stuff has evaporated away. So maybe it's iron-rich stuff near the sun. near the star, and if you're further away, there's definitely ice on the dust. So when we say ice, yes, we can measure carbon dioxide ice, methane ice, nitrogen ice, stuff like that. More questions?
No one would like to grab this opportunity? Okay.
Thank you for the talk. Just more of a personal question.
Mm-hmm.
Throughout your entire career, on a scale of 1 to 10, how happy and satisfied are you with your work?
With my work,
Yeah,
10 out of 10.
it's very good to know.
I'm very happy with what I'm doing right now. I am now a postdoc for 1 year already. I started in October 2021 in this institute in Heidelberg in Germany. So I'm really lucky that I got there. So I also recommend if you want to study astronomy, Germany is a pretty good place. Yes, the quality of education is high, and I think you don't need to pay too much for tuition fees. But one recommendation is try to learn some German before you go there. Yes. My research institute, they have opportunities to do short-term internships, or you want to study a master's degree program with them. PhD program is also possible. So they have calls for that every year. So I think it's around September, roughly, it will be the application, the beginning of the application, so you can look out for it. So my institute is called Max Planck Institute of Astronomy. Don't be confused, there's a Max Planck Institute for Astrophysics as well. That's a different one, they have different focuses. So if you're interested in planets, or you're interested in studying what happens inside a disk, or how planetesimals form, we are the place you come to.
Okay, thank you, Dr. Ma Jingyi, once again.
You're welcome.
All right, we're heading to the last talk of the day, which will be given by Mr. Lai Hong Chun. The title of the talk is Rapid Space Technology Development, How It Affects Astronomical Activity. Before we proceed to his wonderful talk, allow me to briefly introduce our speaker. Mr. Lai is currently a PhD student in Beihang University, majoring in Man-Machine Environmental Engineering. He obtained his Bachelor of Engineering and Master from School of Aerospace Engineering, Universiti Science of Malaysia. His master research mainly focused in his experimental aerodynamic, while his current research focuses on sustainable energy. Though Mr. Lai field isn't in astronomy, he has a great interest in astronomy. He is currently a committee member in Astronomical Society of Penang. He actively participates in the society outreach activities. He is also the presenter in ASP Monthly, APOD sharing session at the end of every month. In Mr. Lai's talk, he will be sharing about the rapid development of space technology that had been happening for decades. Many efforts have been invested to develop new technologies in order to make flying higher, further, safer, and cleaner. With the aid of current technology, humans are allowed to travel into space to conduct research, but also made interplanetary mission possible. Let's welcome Mr. Lai onto the stage.
Okay, so good afternoon, everyone. So I'm Lai from Astronomical Society of Penang. And today I'm talking about rapid space technology development and actually how this development affects the astronomical activity in our life, right? So before I start, all right, I like to share a quote from this Professor Ai Guoxiang, which he said that he made a statement like this: astronomy should actually break through the thinking that there is nothing to be done in space, but truly understand the strategic relation between astronomy and space technology to adopt feasible and sustainable strategies to promote development in astronomy. Basically, it means that we need to combine space technology and astronomy for us to go further. So, textbook, we see Earth, it looks like this, right? But as of January 2022, right, the number of satellites orbiting Earth, all right, the active one and those that mission have ended, all right, is 8,261. And the number of active satellites are actually 4,852, all right? And this is how actually it looks, where from the range from 100 kilometers, where we define space, to the furthest orbit, which is around 36,000 kilometers, which is the, we call it geostationary orbit. All right, so Earth, all right, our Earth is actually fully surrounded by satellites or by space objects. Maybe you might think that space technology is actually quite far from us, all right? We are just a student. We actually don't have much chance to involve or to use all these space technologies. But don't worry, actually space technologies, all this stuff are just besides us. All right, so GPS, all right. I remember when I was a young kid, all right, that time I don't have GPS. So when we travel outstation or to some other countries, the first thing we reach the airport, my parents will get a piece of map of the locals or of the site. But now with smartphones, with GPS, with navigation, it's easy. You have internet, you can go everywhere, right? And then the infrared thermometer, all right, especially now, right, this period when I think especially last year, when we enter every shops, we need to measure your body temperature. So these are the infrared thermometers. It's actually a product of space technology, all right, and diapers. All right, every kids, I think you used diapers before, right? And then internet and communication, all right, now people nowadays it's difficult to survive without internet. And dehydrated food, especially I think university students, you all always have supper with Maggies, right? These are dehydrated foods, all right? A way to preserve food, because you can't bring fresh food into space, especially into ISS. Right, the crew stay up there for 3 months, all right, 90 days or 100 days, and then they need to eat. And they can't every day supply fresh food up there. So dehydrated food. And then the miniaturized cordless vacuum cleaner. Actually, the miniaturized cordless vacuum cleaner we use today is the development for the Apollo mission, for the crews to bring up some moon soils, moon rocks, all right? And after that, when they come back slowly, this is slowly developed into a vacuum cleaner we use in household. And also scratch-proof glasses, all right? Scratch-proof lenses. Scratch-proof lenses is actually applied on the astronaut helmets, right? Astronaut helmets. So these are the space technology that actually benefits us, and it's not far from us, right? But, all right, but how it affects or how it contributes to astronomy or astronomy study. So first, I think we are familiar with this space telescopes. So why we need a space telescope? We need a space telescope because we are observing from Earth. We are experiencing this, right? The turbulent motion in different layer of air, all right, will cause some blurring effect. So to avoid this blurring effect, right, we can send the telescope into space. So the visible wavelength that makes through Earth's atmosphere, but the turbulence in the atmosphere actually causes the image of the star to be blurred and spread out at least 0.5 inch. So even you observing from the best site in the world, all right, this is the effect. So we can have a look on the images, all right, photograph obtained from ground, all right, from astronomers, from Hubble telescope and the James Webb Space Telescope. The James Webb Space Telescope was the most recent one, right? And then the Hubble Space Telescope was launched in the 90s, right? So these are the comparison, all right? So Hubble telescopes range from UV to visible light. I think includes a little bit of infrared, right? And then for JWST, it's actually from visible light to infrared. So this is a difference in image, right? And then our Earth, we have atmosphere. This atmosphere is actually like a filter, like protect us from all the spectrums from universe. So the spectrum that can pass through the atmosphere, basically the radio wave, all right, part of infrared, and then of course visible light, and also part of UV. And the rest like X-ray, gamma rays, microwave, all right, they cannot pass through. All are blocked by our atmosphere. But all these spectrums actually exist in the universe. It's difficult for us to study from Earth. So we need a space telescope, all right, to collect all, that we send into space to collect all these signals and then to have a further studies on all this, about the universe. So examples, right, we have the Chandra X-ray telescope, and we have the Spitzer Space Telescope, which is working on the UV range to sub-millimeter, and then the Hitomi X-ray telescope by Japan, right? So besides space telescopes, and then we go further for interplanetary mission. That means we send spacecraft or we send probes to other planets in the solar system. So why we need interplanetary missions? Because first, it allows scientists to prove or disprove the scientific theories that develops on Earth. All right, scientists, they don't go to other planets to study on what happened on the planets. All right, based on their observation and a little bit, all right, a little bit of imagination and theory, all right, on what the theory that they studied, and they come up with a more developed or a more complete theories on other planets. So everything is done on Earth. So we need to send something to that planets so that we can prove whether our theories is correct or wrong, all right, or disprove it. And then also to gain knowledge that could not gain by observation from Earth's surface, from the orbits around the Earth. And sample return mission, all right. So for example, we have the Hayabusa lander, all right, that lands on an asteroid, all right, for sample return and then came back. And then also the Rosetta mission, it lands on comet. And the New Horizon mission, of course, is the famous one that already left the solar systems and go further. All right. Other planetary missions, all right. So to get a more thorough understanding on the topography and the geography of the planet, the composition of the materials, like for example, we send lander to Mars to see what are actually the composition on the Mars soils, right? And then the climate in Mars, the climate on other planets, all right, the atmosphere, the magnetic field. For example, the Juno mission, right? Juno mission, we have this magnetic sensor to study the magnetic field on the on Jupiter, and also whether existence of water in that planet. Why existence of water in a respective planet is important? Because it might shows that, or it might be the evidence that life might exist on the other planets, right? So, of course, some missions are relatively simple, right? They just want to get some closer image on the planets to study the topography of the planets, all right? And also some are proof of the concept, all right? The most famous one, I think the most famous or recent one is the Ingenuity helicopter by NASA, which was launched in 2021, all right? This is the first unmanned flight in Mars. So this is the Ingenuity, it's a proof of concept, whether we send some aircraft to Mars and whether it can work well in Mars or not. Next, we also have exoplanets search mission, all right? Why we have this exoplanet search mission is basically, in layman terms, we are looking for aliens, okay? So, exoplanets search mission actually is a clue for us to understand whether life exists elsewhere in the universe. And also, we study exoplanet search mission, we can understand how a star or a planetary system form or evolve. So up to date, all right, as Dr. Ma mentioned just now, there are over 5,000 exoplanets discovered. So I just checked just now, it's about 5,241, and it's basically discovered by these three main missions, all right, the Corot mission, which from 2006 to 2014, and then the Kepler mission, which currently holds the record of exoplanet discoveries. All right. The number of exoplanets confirmed by Kepler is 2,710, and yet to be confirmed still at 2,054. And the confirmed exoplanet by TESS is 285 for the time being, and it has discovered about 4,074. But this number are yet to be confirmed. All right, the numbers, all right, they might discover similar planet or the same planets by Kepler or the others, all right, or that might be repeat. So the number not yet confirmed. But what we can make sure is this number will keep on increasing, all right, this number will keep on increasing. And with this number, it's fair or it's not fair to declare that alien does not exist, right? So extraterrestrial life might exist somewhere else in the universe. Right? So there are people studying on this astrobiology, where there's one called the Drake equation that predicts where where life exists, or the probability of life exists in somewhere else in the universe. So next, these are the good sides on space development, on astronomy. But what are the bad side or the impact? All right. First, the increasing number of satellites harm astronomy. So as reported, we have 8,000 over satellites orbiting the Earth for the time being, for now. But all these satellites, will it affect astronomy? Of course, yes. Right. First, optical and near-infrared telescopes will feel the impact. Why? Because we do observation. And when we do observation, for scientific research, in many of the times, all right, it actually requires a uniform quality to the sky to achieve the objective, the research objective. So when satellites up there, all right, some satellites it emits light or reflects light from the sun. We see the satellites. It's actually disturb or interfere the results or the data we obtain. So it is a big challenge, especially for the post-processing of the effective image. All right. So you have the partially remedy problems. So for example, if you have the bright trails, it may cause saturated to the detectors. So portion of the images are unusable. That means we cannot use. But if we remove the fainter effect, fainter satellite trails, all right, it will give us some effects on the. It will leave some residual effects, all right. Actually, seriously affect the importance of scientific programs. So scientists sometimes we have some nice imagination and we have some nice hope, all right? We hope for something. We hope that it would be great if we can have some great computers that help us to eliminate all these noises or all these unwanted satellite trails. But actually it's not easy, all right? It's not easy. Next, on radio astronomy, all right? Optical astronomy, we feel the impacts. But in radio astronomy, all right? Radio astronomy, we don't take images, we take signals, right? We don't observe at night, so we won't see the obvious satellite trails. But the visibility issue is on a different way, all right? So the main problem is actually from the signals that's transmitted down to Earth from the satellite. So satellite, it don't have to pass through the telescope or the radio telescope, all right, to cause interference, all right? If far away, the signal emits in all directions, it will affect the signal collected by the radio telescope. So the cumulative background electromagnetic noise, all right, will cause issues or cause problems to the data. And for this, all right, so there are a lot of radio astronomers, all right, I believe, they actually request to have this protection against the interference, which actually called the spectrum management. So the radio communication sector of International Telecommunication Union actually creates regulation to protect the astronomers studying certain frequency and range of wavelength. All right, so over here there's an image, all right, it's actually signal pollution by the Starlink. Starlink, we know that it's actually by Elon Musk, SpaceX, that they plans to send 12,000 satellites for communication purpose. And I believe professional astronomers, we have no objections on sending satellites for communication, but I think we should have it, I think, the minimal number so that it don't really affect the studies of astronomy, right? Also, besides impact on astronomy research, another main issue on this space technology development brings us the next issue, which is the space junk or space debris. The United States Space Surveillance Network reported that there are 21,000 and that about 22,000 artificial objects orbiting Earth, all right, and including those actively operating satellites. And for space debris, which is less than 1 cm, which is very tiny, all right, not even 1 cm, it's actually more than 128 million pieces. And on Earth, all right, if you throw a small piece of dust or particles with, or small piece of stone with a diameter less than 1 centimeter, it hits someone, it hurts a bit, all right, it won't hurt much. But in space, everything travels, the basic unit is kilometer per second. So it can easily penetrate through a thin wall. So you can see 1.2 centimeter pebbles, all right, traveling in speed of 6.8 kilometer per second, impacting on a sample with 18 centimeters, all right, it can penetrate about half of the thickness. So that means at very high speed, all right, the impact is hazardous, all right, and it's harmful. So this is example of the damage caused by the space debris on the Hubble Space Telescope. And for ISS as well, it actually also, all right, injured by a lot of space debris, all right. So to save these satellites from, or to avoid satellites from injured by this space debris. All right, because space debris sometimes are uncontrollable. Most of the time are uncontrollable. All right, that means it's already a small piece or break into small piece, or the mission ended. We have lost control on the satellites. So what we can do is only we maneuver or we control what we have control on to avoid the collision. So we call it the collision avoidance maneuver. All right, and every maneuver in the space actually increase the cost. All right, so making the mission become more cost ineffective. Right, and of course to astrophotography. So of course the good thing is we can get beautiful satellite or space station transiting images. All right, and what I understand from our members from ASP that do this astrophotography, they say that obtaining image or capturing image for ISS transit is more difficult compared to capturing image for solar or lunar eclipse, right? Because all this happens, all right, the transit happens in maybe the longest a few seconds, or some is just 1 or 2 seconds. So in 1 or 2 seconds before that, you have to prepare everything well prepared so that you can get this nice image, all right? So this is the image by Dave Keefe, where ISS transiting the moon, while the other one is by Thierry Legault, is the Chinese space station, Tiangong transiting the sun. Okay, so besides the satellite or the space station transiting images, all right, we can have space entertainment. All right, for example, I think in 2017 or 2018, where same in this hall, Komcha, I think. All right, we have the CEO from L, a Japanese company that working on space entertainment. All right, she studies on artificial meteors. Right, that means she sends a satellite to LEO orbit and then release the pebbles or the capsule that will decide the colors of the meteor. So artificial meteors. All right, and then China actually sent the Ladybird 1 satellite. All right, and they use it. Okay, this is image captured. The satellite actually released light trails in the form of Morse code. All right, so they use it. This is an image on the 7th of July of the lunar calendar. All right, that one is the Chinese Valentine's Day. So they send a message called 对象, 你拿来吧. That means translate, it means is something like they are looking for, or it's like showing showing the, how to say, that means we showing or presenting the love to someone. All right, and this is the Ladybird satellite trail across the sky. All right, the sky is dark enough, and then they have the trails over here. So it's in the form of Morse code. So this can be the nice part, all right, the interesting part for space entertainment. But, all right, the satellite trail sometimes is quite annoying, especially when you're trying to taking like star trails or night skies, and then with certain time of exposure, and then you will see all these streaks, which is for those people with OCD, maybe they are annoyed or they are not happy with this, all right? So these are the star trails image by Alan Dyer, and we realize that there is a satellite trails, and also the night sky by Egon Filter. This is a comet, all right? This is a comet. Sorry, not comet, this is a meteor, but this is the satellite trails, and not only one, there are a few, right? So this is the effect on satellite trails, light pollution. And a short conclusion, so basically, the study or the research on astronomy starts with naked eyes in the ancient days, right? Ancient Chinese, ancient Egypt, the Mayans, all right? They observe through naked eye because they don't have all these equipments. And then we develop telescopes, and then we start to have a closer look on the moons, on the planets. And then with space technology developments, we have space telescopes, we have landers, we have all kinds of satellites. All right. So the development of space technology made study of universe in all spectrum available. And space technology actually brings the level of astronomical research into a higher level. But attention is required for space environmental issue. I think the authorities, the satellite developers and astronomers, we have to make something, all right, or we have to do something on the issue caused by this space technology development on astronomy. And the effects is also very significant towards astrophotography. But we have discussed of all these issues, but are these the major challenge faced by Malaysian astronomer? To me, I think there's another major issue, right, which is these clouds. We are in a tropical area, we are in a tropic country. So 365 days a year, I think we have at least 360 days of cloudy nights. So if you're lucky, all right, you're lucky, the clouds only cover partial of the sky. You can still see some planets or some moon, you can see the moon. But if you're unlucky, all right, everything is covered up. All right. So lastly, before I end my presentation, so this is a statement made by Professor Deborah Elmer-Green, the president of International Astronomical Union. She said that interference of our view of the sky caused by ground-based artificial lights, optical and infrared trails of satellite constellation and radio transmission on the ground and in space is existential threat to astronomical observation. Viewing the night sky has been culturally important throughout humanity's history, and dark skies are important for wildlife as well. All right, so that's all for my presentation today. Thank you, and we hope for a nice, clear sky tonight for the stargazing. Thank you.
So now it's Q&A session again. So please move to the nearest microphone if you have any questions.
Hi. Hello.
Hello.
Thank you for the great speech. I have a question about space telescopes.
Uh-huh.
So, can space telescopes detect the gas composition of other planets? And if they can, how do they do it?
Space telescopes, it actually can, because we have space telescopes in different wavelength. All right, some they study the visible light, some they study on infrared, some on UV, on X-ray, on gamma rays. So I believe all these particles in the universe, they actually emit or give out or reflects or absorb this electromagnetic spectrum in the space. So all the reflected signals or all these spectrums collected by different types of telescope in space, like the ultraviolet one, the X-rays one, the infrared one. All right, and through that we can actually detect something up there. All right.
Any more questions?
Hello.
Hello.
May I know how does a star trail form?
Oh, star trails form. All right, the star trails form is actually quite. It's not form actually. It's actually because we have a camera. All right, we capture the night sky. Right, so we open an exposure maybe for like 1 minute or 2 minutes or 30 seconds. All right, and the stars in the sky is actually moving. We don't feel the movement because they are very far away from us. So the motion is actually not big to our naked eye. But if you open the exposure for long enough, then you will see the trails. All right, the exposure long enough, you'll see the trails. All right, so maybe you can try out tonight if we have a good sky, you have a good camera, you can try out, right?
Okay, thank you.
Thank you.
Okay, so thank you, Mr. Lai, for such an informative talk. So we have come to the end of our fall talks. Before we close, we would like to invite Dr. John onto the stage to give small token appreciation to the speakers. Now, please welcome our speaker, Dr. Ma, onto the stage to receive the token of appreciation. Thank you, Dr. Ma. Next, please welcome Mr. Lai onto the stage to receive the token of appreciation. Thank you, Dr. John and Mr. Lai. So we are now officially end with the talk session. We'll see you again tonight during the event and evening with astronomers. Please stay tuned. Thank you.